I'm Andrei, and we will spend 1 hour together for talking how we can find vulnerabilities in software using open source tools. I want to mention that if you have any question during the presentation, please feel free to interrupt me and we can discuss. Let me start by a bit of context about myself. I started an open core startup 1.5 years ago with a bunch of friends. And after working on it, participating in different programs for startups, we decided to stop it because of lack of traction in the open source space and business space. And this also come with the decision to leave the previous job that I had, which was in the army, in the Romanian army to be more precisely. And this is the photo that I had from the last day in the server's room. After that, I was lucky enough to enter Canonical in the Ubuntu security track for securing the distribution. This is a photo with my team in Bilbao, in which we participated in the Linux Security Summit and a physical sprint together. At the same time, thanks to Alex Murray, I started doing short sections in the Ubuntu Security podcast for detailing academic papers. So if you want to hear that out, just give a try on Spotify or whatever podcasting platform you prefer. So let's deep dive into the content. Open source implies the code is open, namely anyone can read it. And this also assumes the ability of an attacker to read the code and to detect vulnerabilities and to exploit any instance that are set by anyone on the internet. But in my opinion, this doesn't need to be this way. We already have some open source tools that we can install and detect these vulnerabilities before the attackers, namely in a shift left approach during the development of the code. And this will also minimize the risk of publishing vulnerable software on the internet. And let's start with an example, which is for Roundcube. Roundcube is a browser-based IMAP client, and as in their websites, it provides full functionality you expect from any email client, for example, Outlook or Gmail. This is a graph with their GitHub stars just to get a grasp of the adoption of the tool in the open source space. You can see that there is a steady increase of the stars, so the software, in my opinion, is widely used in practice. And you can also judge this Shodan query. For anyone who doesn't know this, Shodan is a search engine for computers on the internet. You can create a query, run the query, and after that, Shodan will provide you a list with all hosts on the internet that will match the query. So by using this simple query, namely http://component roundcube, we can see that there are 161K hosts on the internet. So this somehow prove our previous assumption. After that, we can look at what programming languages do we have for this code base. And what I did here is just cloning the repository, changing the directory into what I already cloned and running SSC into the current folder with a head. And we can see the top programming languages in these code bases, and there are PHP, SQL, JavaScript, HTML. If anyone here has a home lab, maybe this is familiar for you. This is the web installation page for Roundcube. And basically you can plug a lot of details in your browser, and this will be stored in the server. What happens here, it's detailed on this diagram. Basically, we have the user, which configures the Roundcube instance through the user interface. The raw user-controlled configuration is stored on the internal configuration. And after the initial configuration, if anyone sends an email with a non-standard image, then we should get the path to the conversion program, which is set in the initial configuration. And we need to execute Roundcube exec for converting that image into something that Roundcube understands. So basically, we have two main flows here, one for installation, one for email processing, which is basically the vulnerable one. And I want to ask you if you have any idea what's missing here, judging by this raw user-controlled configuration. Yeah, that's right. And any other aspect that's missing? Input sanitization. Maybe it's not important enough that the user is not authenticated, but we also have the problem of the input not being sanitized. Namely, any command that is executed here in the last execution path is basically user controlled by anyone on the internet. So an attacker can send a post request to the installer. You can see there an convert path with a PHP command, which is for a reverse shell. After the attacker sends an email containing an image with a non-standard format, for example TIFF, that Roundcube doesn't understand by default, Roundcube will try to convert the image to JPEG using the command that was provided when configuring the instance, which is the parameter of the convert path. So in this way, the attacker will have a reverse shell. Basically, anyone from the internet can scan for hosts, can send this kind of requests. After that, can send an email with a non-standard image and get reverse shell into these instances. This is known as CVE 2020-12641. There are multiple configuration items as the one that we previously saw, as convert path, which led to arbitrary code execution into the instance. The CVSS for this vulnerability was 9.8. It has an exploitability score of 8.1, which is pretty high. So basically, if you have a vulnerable Roundcube instance on the internet, there is a high probability of you being exploited. And as previously saw during the last year, this was also used by APT 28, which is this advanced persistent threat actor, a huge name in the bad guys scene, which compromised Ukrainians' organization servers during the Ukrainian-Russia war. And it was also added by CISA, which is this American organization, into their known exploited vulnerabilities catalog. And then the question is, was this preventable? What do you think? Yes, it was, but there is a but, not with standard linters and scanners. As you previously saw, there are some functions, for example, Roundcube exec, that, for example, Bandit or CPP check or any other linter will not understand by default. This is basically the vulnerable function, which doesn't do the input sanitization that we previously mentioned. And you can see there, for example, after that command, executable must exist, that if that check will pass, then the command is returned as it is, basically the raw user-controlled configuration, without any shell escape, let's say. One possible solution for this is taint analysis. We will discuss this in a following section. Basically, we will track the execution flow using this source of data, namely Roundcube get instance config, and we will set a sink, a sensitive sink, namely, hey, if this data will end up into this sink, for example, an argument into a function call, then we have something sensitive in there. There is something named semgrep, which is this code querying engine. We will discuss this in the presentation. And this is a rule, a YAML rule that is created for semgrep for detecting this vulnerability. We basically set the source using a pattern with the function and the object that we previously mentioned, the sanitizer that must exist in order for data to be sanitized, in this case, escape shell command, and the vulnerable sink, which in this case is return. And if we run this rule, the semgrep rule over the function we saw before, we will have two matches here. Basically, the returns of command without any sanitization function called. So what I want to detail today is the open source fortress. There is an internet-facing website in which the whole presentation and the workshop that backs this presentation are. Um, there is basically a collection of open source tools that you can proactively use to detect vulnerabilities in your code bases. And there are multiple sections here, namely factual information about software security topics, and the brief presentation for each analysis technique, and some practical examples, namely some exercises that you can do at home for testing these tools on your own. This presentation will cover only the bolded items in here. I hope the quality of this is good enough. Judging by the smiles is not, so let's take this one by one. We basically have there as the first step threat modeling. Namely, we need to think about how an attacker can attack our application. After achieving this process, we will have a threat model. For example, if we have a login page, we can think, hey, maybe anyone on the internet can brute force this. There is a threat there, so we should consider this in later development phases. After that, there are two branches here, one for manual vulnerability detection, namely myself as a security researcher will do some manual steps in order to detect the vulnerabilities in that code. And the other approach, that is the bottom branch, is for automated vulnerability detection. And here we have multiple steps. The first one is running the tool and aggregating the results. After that, we have triaging, namely seeing what warnings are invalid or not. And after that, in the end, we end up with some vulnerabilities that are coming from both processes, namely the manual and the automated one. For the second one, for the second approach, you can also think about a CI/CD pipeline in which you have some quality gates. For example, hey, after each PR that I receive for my code base, I'm running a lot of linters and security scanners for seeing if that commit is vulnerable or not. If it's not, I'm merging the changes into the main branch. After having these vulnerabilities, we have two approaches, either to execute the defense activities, if, for example, the code base is ours, either to attack the code base if we are a malicious person. For defensive activities, we need to research the vulnerability. For example, if you have experience with AFL or any fuzzer, you can detect crashes. Basically, some blobs of data which doesn't mean anything. You only know that the program is crashing, but you have no further context. So in this step, you basically need to take the data that is crashing the application and do some research in order to understand why your application is crashing. This also contains CVSS approximation. You can see there a string. Basically, there are multiple components for computing a score between 0 and 1, which is the severity of the vulnerability. And this is, for example, for log4j. And you can see here in the end something like CH, IH, which is configuration impact high, integrity impact high, and availability impact high. Beside this, we have CWE, which is basically a classification of the vulnerability. In the case of log4j, we have this CWE, which is 502, which stands from deserialization of untrusted data. You'll have the presentation afterward. The links are clickable, so you can deep dive afterward. And we should also request a CVID. For example, if I'm the maintainer of OpenSSL, let's say, I want the users of my library to be concerned and to update their libraries. So what I'm doing is to publish this CVE, which is basically an identifier and a bunch of information about the vulnerability itself. In the case of log4j, there is this unique string that may be well known for many of you. And other defensive activity is patching. For example, this patch that is linked here from Oracle, communication with stakeholders, and this is the remediation guide from Apache. And as previously mentioned, you can also do offensive activities. For example, if you want to write a malware, and this is not something that I'm proposing, but this is something usually done by state actors, by anyone wanting to spread the malware in the wild. And there are multiple steps here. You need to write an exploit. You need to detect an attack vector. For example, we can continue the example for Log4j. Here you can target VMware Horizon instances and exploit Log4j. You can bypass mitigations, and here we have two TTPs, which are for symmetrically encrypted channel communication and mimicking legit services. Again, there are links in the presentation for afterward. And weaponization, yeah, an ID for a TTP. And yeah, the exploitation part in which you basically run the exploit over instances on the internet. But we will look today at Ubuntu Portrait, which is a vulnerable by design code base, like WebGoat, like then vulnerable web app, like CloudGoat, any vulnerable application that is written to be vulnerable by default. Basically, it's a lightweight piece of software that runs on an Ubuntu server and allows users to control it through their browsers. I written this from scratch. It contains a lot of vulnerabilities, and basically we will look at multiple techniques in which we can detect vulnerabilities in the code base. It should be deployed on premise, and it's written in Python and C. So most of the tools are specialized on these two programming languages. There are 12 plus embedded vulnerabilities, and there is a plus there because the application depends on Python packages. As you know, vulnerabilities appear during night, so maybe there are multiple vulnerabilities appeared in the meantime. Let me show you how this look. Basically, here we have a login form in which I used the PAM credentials. I want to upload the file in the server. I'm clicking some buttons, and there is also a functionality for exploring the file system. And I'm showing you this to provide you an idea about what's the application about, and yeah, just to let you think about what can go wrong with this application. For example, you've seen some a way to execute commands. What if we can run commands which are not embedded in the sandbox? This is the architecture of the application. Basically, we have a web UI which does API requests through HTTP to a backend, which hosts a web API in Python 3 and Flask, and it also connects to a shared object written in C for generating recovery tokens, and the Linux authenticator for checking if the provided credentials are valid or not. Nice. So the first technique for detecting vulnerabilities, or a proactive step, let's say, not really to detect vulnerabilities, but to catalyze the action of detecting vulnerabilities, is threat modeling. And this is an image perfectly illustrating what threat modeling is. We have some assets, which is the food on our fridge. We have a threat for our assets, which is the cat, which is trying to get the food. And threat modeling means being inspired enough to assume that the cat will want to steal the food from the fridge. So, as previously mentioned, it means identifying the assets and the threats. So you should answer to these questions for your code bases. What we need to defend, what can go wrong, and I should mention here that this threat modeling activity is already a legal requirement in some states, for example, USA and Singapore. Not all states are adopting this at the moment, but in my opinion, this will be the future. And there are multiple advantages for this kind of approach for threat modeling, namely to design a secure by default solution, to prioritize your activities, and yeah, to boost the confidence of your stakeholders. Because as you see, some states are requiring this, so they want to have confidence in the solution you develop. The first open source tool we will look at is OWASP Threat Dragon. Here is a quick demo for Threat Dragon. I'm creating a threat model here. I'm already using something existing, but after clicking the existing model, I can see the architecture items, for example, the circles and the rectangle on top, and some details on the bottom for explaining what each component does. And the red lines over there are existing threads. For example, I have an authentication path, something there may happen wrongly. So I should think about that and plan for some mitigations. So the usual process for this open source tool is creating a threat model using a diagram style. In this case, in OWASP we have stride and CIA. We need to represent our assets, which means which can be stores, processes, actors, data flows, and trust boundaries, and to manually identify the threats which are possible with type, status, course, priority, description, and mitigations. There are, for example, some commercial tools which automatically identify the threats which are possible. For example, hey, I'm using these AWS components, I'm linking these two together, what can go wrong? And the tool will automatically detect the information without you being required to do this manually. Do you remember this image? Any metrics fan here? No? So there is this search scene in metrics, and this is an illustration for the next vulnerability detection technique that we will look at, namely code querying. It means searching for a specific pattern into our code base, and there is an optional abstract representation of the code base, for example, as abstract syntax tree or control flow graphs. There are multiple query types in here. You can search for literals. For example, I'm searching for scanf, but basically I can have, this is a dummy approach. Basically you can have scanf into a comment and it will also match. You can have regexes, and basically I'm writing here some parentheses for detecting the calls. This is still dummy, but I also have some data structures. And there is a tool called Journ, which has a specialized kind of query language. And after creating an abstract syntax tree, it provides me the ability to query that tree. So I can write here CPG, which is the graph, that method, and I can search for scanf, and after that, all calls. And the advantage for this technique for code querying is that you can have community queries, which are generic, but they can help you detect some vulnerabilities for which you are not aware of. This is an example of an abstract syntax tree. This is what a computer or compiler will understand. So we need to think about ways in which we can query it. For this, we have semgrep. The installation process is pretty straightforward, just pip install semgrep. After that, we need to write this kind of YAML rules. There is the first example regarding Brown-Cube. There is this one for detecting all login calls to logging or logger using some passwords or tokens. So we are trying to detect all passwords or token which are logged by the application, which, as you assume, it's a vulnerable pattern. We should not do this in our code bases. After that, I'm running semgrep with the scan functionality. I want to export the results into the serif format, which is something proposed by Microsoft for standardizing the results of static analyzers. I'm mentioning the configuration path, where should I store the output, and what's the code base. In my case, there is the portrait application, the one which we described 5 minutes ago. After running the tool, I can see that 17 files were scanned, and that there are 9 findings, namely 9 vulnerabilities in this code base. And this is a snippet from Ubuntu Portrait in which, in fact, the user and password were logged after authenticating a user. You can also test this at home using semgrep and the code base of this workshop. What is semgrep? It's a partially open source code scanner. I'm saying here partially because they are an open core startup. They have an open source solution, but they also provide some pro feature that for which you should pay for. It supports 30 plus languages. There are no prior build requirements, and in my opinion, this is a huge advantage. You have, for example, Coverity, but Coverity has this disadvantage that you should build firstly your code base, and after that run the tools. For semgrep is not the case. It's basically scanning the code, and that's it. And another advantage for semgrep is that it has no DSL. If you remember the journ query, you have seen that there are multiple weird names that are combined, and after that you have the query. For semgrep, if you want to query, for example, Python code, you'll write Python code in the end. So it's low barrier to entry. And the advantage that was previously mentioned, namely it has default rules, basically a default configuration that you can use for scanning your code bases, but you also have third-party rules, which are written by members of the open source community that you can take and run on your code bases. The next technique, yeah, another classic here, guesses? Idiocracy for 2005, in which people are dumb enough to not being able to solve this kind of games. And the question here, what if we can have the same approach, the same dumb approach for our programs and testing our programs? And this is what fuzzing does. Namely, hey, let's run the program using some random inputs and see what happens. In this case, a crash in the program is basically a security issue. This may or may not be the true statement. For example, we can catch null dereferencing. We can have sanitizers as address sanitizers, undefined behavior sanitizers for increasing our success rates. And basically, it's a BFS traversal of the control flow graph. And there are multiple optimizations here for running our code faster, which is instrumenting the code or, knowing the input format, which are helping the fuzzer to do a better job. This is the architecture of a fuzzer, but we will not deep dive into that. Maybe leave it for home. And as an open source tool for implementing fuzzing in your code bases, you can use AFL++. There is a straightforward installation. You basically need to run the Docker image and that's it. And this is a harness, namely some code that we should run beside the code of the application for gluing the fuzzer and the code base. And you can see here that we have a file that is read, basically the file that is produced by the fuzzer, and in the end there is a call to generate recovery token, which is the function that we want to fuzz. So basically we run that function using 2 arguments which are generated by the fuzzer. This is how we can run AFL. Firstly, we need to compile our program with using AFL-CC. It's an alternative for GCC or CLang or whatever you use that basically implements or instruments the code base in order for the fuzzer to do a better job. We also include the symbols using the -g flag. We specify which is the executable that we should produce, which is crashmeifyoucan.elf, and the C source files which are used for as input. After that, we run the fuzzer, which is AFL fuzz, with a -i flag for specifying some dummy inputs. For example, if we want to fuzz a parser for images, we can provide some example images for the fuzzer to better understand the format, -o for specifying where the output should be stored, and in the end, the executable that we should fuzz, and a symbol for specifying where the fuzz data should be placed, so as an argument in this case. We run the program, and we can see that after some milliseconds there is the first crash. You can look at the findings in depth section, and there is a total crash number which is 1. And this is the code that triggered the crash, and you can see here that there is a buffer which has a fixed size in which we copy the data which are specified when calling the function. So basically, this is how we can use a fuzzer to detect vulnerabilities in this kind of complex code, which is, in my opinion, hard to audit manually, or hard to understand if you are not the writer of the code base. So this was a demo for AFL++. It's a fork for American Fuzzy Lab. And it has, besides AFL, some additional features, which are QEMU emulation, persistent mode, which help us to create snapshots of the process and run the program faster and faster, and other optimizations. And it's nice that Google already embedded this tool into OSS Fuzz. So if you are a maintainer, just a short introduction here, if you are a maintainer of an open source tool into a memory unsafe language, you can basically create a PR for OSS Fuzz for integrating your application into their fuzzer, and they will allocate the Google infrastructure to fuzz your code. So basically to detect vulnerabilities using in your code, which is pretty nice, and there are a lot of huge projects in the open source space which are already leveraging this, and they have nice trophies, nice vulnerabilities which we're detecting with this approach. Another technique for finding vulnerabilities is secret detection. And there was, I'm Romanian, in fact, and we had this habit for hiding our keys under our mat, which is really insecure. Basically, a thief can look under the mat and detect the keys. And we try to transpose this approach, namely finding the keys under the mats, in computer science, into development. And we have here secret scanning. There are multiple types of secrets into a code base. We have API keys, we have credentials, we have tokens. These are sensitive items which should not be included in your code base. You should use, for example, environments variable or standard input or whatever you prefer, but not including them into your Git repository, let's say. This approach means scanning for a specific pattern or for entropy for a secret. And as for the case of code scanning, we have here community or generic rules. For example, there are some rules which are created by the community for scanning for AWS tokens. You can import these for your code base and run them, and that's pretty much it. There is low effort. For the practical part and the next open source tool we will look at, we will download the release for Git leaks. You basically need to enter their GitHub and click the release tab and download the binary for your architecture. The run is pretty straightforward. Just use this command that will specify where the source code is stored, and where the results should be stored. And the last flag is for reducing the secrets. Basically, the results will not also include the secrets, only their location. After running this tool for multiple commits, we can see that there are 5 secrets which were leaked. And this is something for Ubuntu Portrait, the application at the first of the presentation, in which I included a secret key for Flask. This is hard-coded. I should have used, for example, I don't know, some random number generator that is present in my operating system, and not using this approach of having a hard-coded key. So Git leaks, it's a detector for hard-coded secrets. What's nice about this tool is that it's analyzing the entire Git history, so not only the current state of the code base, also the commits in the past, because, for example, you can have overwritten secrets. You may think that they will not exist in your code base, but in fact, someone from the internet can scan all commits and can detect them. And it also supports baselines and custom formats for secret. For example, if you have a custom API, and this is something that GitHub does, for example, they have a prefix, for example, JH underscore, and after that the secret. You can also have this approach for your secrets, prefix them with something, and after that create a pattern for a secret scanner, and in this way you can detect your custom tokens. And the baselines, what this means, these tools have maybe a high rate of false positive. So you can run the tool once, validate the warnings, and after that, consider all warnings as false positive. If you run the tool again, you will exclude the warnings which you already proved as false positive. So you only scan for the difference, and you should validate only a few warnings of the tools. I have this XACD meme for illustrating a chain of dependency, and I think you are already familiar with this because of PIPI, because of NPM. This is a graph that is generated for an NPM package. You can see the main package in the center, and after that there is a huge dependency tree for that dependency. Basically, if we have a vulnerability into one dependency, this will propagate in our code base. But it's nice that we have open source tool to deal with this, namely tools for dependency scanning. We basically iterate through all dependencies in our code base, and we try to find vulnerabilities in them. For example, CVs which are published for Flask that we are using for creating our web servers. It's using a dependency declaration list, for example, a PyProject.toml or package.json in the case of the NPM ecosystem. And for this demo section, we will look at OSV Scanner. It's a tool created by Google, and yeah, as previously, the setup process is straightforward. We just download the binary from the releases from GitHub. We run the tool with this simple command. We just specify the poetry.log file, which is generated by Poetry, a package manager for Python. And we can see a bunch of vulnerabilities which are reported by the tool. I really think that this list increased in the previous few days, so this may be a bit updated. And you can see here the dependency list. In this case, I searched for CV 2023-4863, which was a heap buffer overflow in libwebp, which was in fact used by this pillow library, which I had integrated in Ubuntu Portrait. OSV Scanner, basically there is a database published by Google, the OSV database, which embeds multiple sources, which are GitHub Security Advisories, PIPI, RustSec, and Global Security Database. And there is also support for ignore vulnerabilities. So if you can prove that a vulnerability doesn't apply in your code base. You can specify the vulnerability as false positive. Yeah. So Black Duck, if I remember correctly, is for composability analysis. So maybe the end goals are a bit different. But I can compare to Fossa. I know that they have some reachability feature which is pretty handy in my opinion. For example, they see that hey, you are a dependent of this package, but we will also look at your function calls. Basically, if I'm using a vulnerable package, it doesn't mean I'm also vulnerable. I should call the vulnerable function from that package. So they are also doing this. Maybe we can expect some tools in the open source space in the near future for also implementing this. But yeah, at the moment there are only the commercial providers which offer this kind of features. The next section, I like the car safety or the automotive industry because they have these standards they should check for each car. Basically, they have a score, and based on that score, you can assume how safe the car is in an accident. So we have the same approach in our computer science industry for linting, which basically means defining some rules and do some static analysis for finding issues before compiling or running the code. And these issues may be formatting. For example, hey, you're using spaces and not tabs, or tabs and not spaces, whatever you use. You can also scan for grammar. For example, if a developer is not using inclusive words in the UI, you can basically automatically raise some warning for the developer to replace these words, or you can also have security warnings. For this demo section, we will use Bandit. Maybe this is really familiar for you, for Python developers in the room. It's already integrated in a lot of IDEs, but we will prefer the CLI interface. I'm using the recursive flag for scanning all source files. I'm specifying the path to the code base. I'm specifying the format, which is also serif. This is a common theme in my presentation. I like serif. It's nice about serif that you can also push the results into the GitHub security tab. So it's pretty straightforward, and you can have results into the GitHub user interface with the linters or security tools that you have set. And a -O for setting what the output file is. After running the tool, we can see this output, and there is this snippet from our code base from oops, test. Yeah, it's fine. So this is a snippet from Ubuntu Portrait. You can see there that I'm unarchiving a file, and this is a vulnerable pattern that is already detected by a lot of linters. So it's a low-hanging fruit that is fastly detected by an attacker, but can also be fastly detected by the developers, with Bandit in this case. It's a linter for Python. It has an abstract syntax tree representation of the code, and there are multiple modules in this tool. Basically, we have patterns for suspicious code. We have deny lists for imports or function calls. For example, if we want to block the pickle module, we can do this from Bandit. And it also have a report generating functionality if we want to pass the results to any other person. And it also has supports for baseline, the functionality we already discussed. Another movie. Do you remember this? It's from Maze Runner. Basically, they are locked inside a maze, and they need to run inside the maze in order to detect all paths, and they need to escape the maze. And yeah, we can also think about how we can apply this abstract concept of having a huge problem space and searching it in computer science. And this is what symbolic execution does, and data analysis. We have the CFG, the control flow graph, basically the tree with all function calls in our code bases, and we replace the concrete values with some symbolic ones, and we search for some specific patterns. There are multiple components here. There are some sources, namely where the data came from, some sinks, namely some places in which some tainted data may end up, and we can consider this combination of sensitive sink and tainted source as a vulnerability, and some patterns. And we also have a path explosion problem here. Basically, some code bases are huge. It's really hard to explore all possible paths. We can miss a lot of vulnerabilities, but the guarantee of this approach is that we will explore all possible combinations in the end with, let's say, an infinite compute power, which is, yeah, not true, but it's still detecting a lot of vulnerabilities in projects. As a demo, we have CLI, which is an open source symbolic execution engine. Just take the Docker image, run it. As in the case for fuzzing, you need to write a bit of glue code. In this case, I'm marking some buffers and an integer, a symbolic, and I'm running the generate recovery token function again. I'm running the compilation phase, the engine, and in the end, I can see that I have an error there, namely an out of bound pointer, which is basically the error which was detected previously by fuzzing. So CLI, it's a generic symbolic execution engine with security use cases and built on LLVM. This marks the end of all security detection techniques, but there are others which you may use. There is stress and load testing. You can use JMeter for many protocols and services, or K6 for Kubernetes, and web dynamic analysis using OASP ZAP. And we all like automation, so all this tool can also be automated. I will briefly mention some tools that you can use. There is Sarif multi-tool for performing operations with the Sarif files that we generated into this presentation. We have make and poi the pod for running the tasks. We have ID workflows, for example, something integrated in Visual Studio Tasks for running the tooling while coding. We have pre-commit, for example, hey, run me this bunch of linters before pushing the commit into the origin. And ACT and GitLab runner for running CI/CD workflows locally. This is pretty useful for developing some or using the same code that you want to run on remotely on GitLab or GitHub, but locally. And yeah, the remote alternatives. I want to end this by mentioning the Ubuntu concept, which is, yeah, I guess you are familiar with the Ubuntu operating system, but we didn't invent the name. It's a South African philosophy and ethical concept. And I really like this quote from Nelson Mandela: Ubuntu does not mean that people should not address themselves. The question, therefore, is, are you going to do so in order to enable the community around you to be able to improve? So I want to end this presentation with some ways in which you can help the open source space. At first, you have some sponsorship options. There are a lot of GitHub projects with this button, namely sponsor. You can donate €1 or €2 monthly for the projects that you use. This means a lot for maintainers who are contributing their spare time for community basically. You can also report bugs and vulnerabilities via email, GitHub issues, or any reporting channels that the upstream has. For example, just take a random code base from the internet, from GitHub, run the tools that I described on this presentation, and see what you get. Maybe there are some vulnerabilities that the upstream are not aware of. And lastly, you can implement some features or solve some bugs for security tools, or maybe you can propose some patches for the vulnerabilities you discovered in the previous approach. And in this way, I can bet that the whole community will be grateful for the work that you did. So I was Andrei. If there is a single thing to remember for this entire presentation, there is this link, which already contained the presentation, the workshop, the cheat sheets that you can use, and more. So the barrier to entry in this vulnerability detection space is pretty low, in my opinion. So you can go home and implement these features in a few minutes. Thanks. If
towards the beginning, you mentioned a flaw with a round cube, and then you used semgrep, static analysis tool.
Yeah.
I'm not familiar to show a way of detecting that, but you had to load like a custom rule. I use Coverity, and I'm fairly certain Coverity would just catch that without needing a custom rule. The open source version of semgrep, does it have a more generalized rule that would catch that in other software?
So as previously saw in the code base, there are some custom methods which are called, right? There is, for example, the roundcube namespace, and there is this exec function inside the namespace. The linters and semgrep will not detect this kind of methods by default, so you should specify them. In my opinion, the rules are pretty straightforward to implement. You need just to understand the format for these YAML files, and the open source engine is capable of using the tools that you generate, run the data flow analysis that I mentioned in the presentation, and combine this information and detect the vulnerability. This is something that I use in the practice. So you can use the open source engine with that rule and detect the root cause of the CV that we have seen. Does this answer your question?
So for me, the reason to use code scanners is so I can stand on somebody else's shoulders who's way brighter than I am, because I'm stupid. These open source code scanners and all of this that you're talking about, are they actually maintained by people? Or do I have to go in there and write my own rules to try to figure out my own bugs? Are other people contributing? How active are these projects so that I can, look at this and I can say, look, I'm going to put this in my pipeline so that I'm constantly, getting other people's input and trying to build on their shoulders. Because if they're not, I'm just going to go out and spend the money to buy a commercial version of this because the security of my products depend upon it. So can you comment on that, on what you see as the activity on these various projects?
So the startup that I previously mentioned was for small and medium businesses. And a thing that I learned from that experience was that the small companies that doesn't have the money for the commercial solutions. For example, they can pay 1,000 for a security solution because maybe they have a marketing campaign that they should execute. So in my opinion, you can use this open source tool for tools if you don't have the money or if your use cases are generic enough. To respond to your question, there are a lot of contributions. These tools are used by security researchers, by DevSecOps people, by DevOps people, so there are a lot of of parties integrated in the community, which are contributing with their rules. I'm familiar with SamGrab. There are a lot of people pushing their rules into the open source space, either by using the hosted repository from SamGrab, or just create a GitHub repository and push the YAML rules there. So in my opinion, yeah, you can use Bandit, for example, just run the tool and you can have some low hanging fruits that you can catch. But if you have some really tailored use cases, maybe you can tailor the scanners, which are open source, or if you have the money, pay a provider to do this work for you. And you should also have you should also consider the fact that most of these tools, namely the static ones, so not symbolic execution and not fuzzing, are generating a lot of false positives. This issue seems somehow solved by the commercial companies, but we are still fighting this in the open source space. There are a lot of warnings generated by Bandit, by CPP check, by other tools, so you should invest the time to validate if the warnings are valid or not.
Yeah, just one follow-up question. So the one thing that I didn't see in here is the profilers, where you take your code and run it in a profiler and run your tests against it to make sure that you're actually, squirreling into all of the if statements and execution and stuff like that.
Are you referring to coverage or?
Yeah, code coverage, code coverage profiling.
Yeah, it's a nice recommendation. I will do this, in fact. So the workshop and the websites are work in progress. So it's a good idea. I preferred going to security tailored tools, namely security scanners, fuzzers, symbolic execution engines. But yeah, I agree that you can also use this kind of coverage analysis or profiling to detect the code paths which are not that executed, because if they are not executed, maybe people are not paying enough attention to these code flows. But the attackers may detect that there is a vulnerability there, and they may target that specific code flow. Yeah, thanks for the recommendation.
Okay, so I guess one of the questions I have is, you mentioned going back to OSV scanner. How would you, projects like Yocto have tools for checking vulnerabilities, but they're using the CVE database instead, like CVE check. Would you recommend to one of those projects that they start looking at using this different database, OSV scanner, as opposed to they're just checking CVEs?
They are also checking CVs, but it's nice about them that they are trying to integrate this vulnerability data under the same umbrella. They are doing this, for example, with RustSec. If I remember correctly, there is no direct correlation between a RustSec ID and the CV. They are not working for assigning a CV ID for each RustSec ID. So in my opinion, it depends on the project. If you have vulnerability data which is not available in CV or MITRE or NVD, you should also use alternative streams. Maybe there is OSV scanner, maybe there is another tool which is tailored for your tool chain.
Okay, so this Yocto is a distribution builder. I don't know if you're familiar.
No.
I don't know if, okay. So, they're used for building embedded Linux distributions. It's pretty heavily used in the embedded Linux community. And so I'm just curious if somebody on that side should be looking at switching to OSV scanner, as opposed to I think they may have rolled their own scripts to look for CVEs, and especially if OSV scanner is kind of a superset of CVEs. Is that basically true?
Yeah, but it depends on the superset. I mean, if only the CV is applied to your project, in my opinion, it's the same. It's the same thing to use a CV scanner and to use this kind of aggregator like OSV scanner. So if I'm using, for example, Rust, maybe I have an advantage in using OSV scanner because I have the Rust scanning already integrated,
Right.
and the vulnerabilities are not published as a CV. But if I'm using, I don't know, Perl. Maybe Perl is not integrating in OSV scanner. There are only CVE. So I mean, I can also use, I will only use the CVE scanner because OSV scanner will basically generate the same information in the
Okay,
end.
yeah. No, there is a Rust layer for Yocto. I don't know if it's official or not, but okay, thank you.
Thank you for attending. Please give a round of applause to our speaker.